Welcome to our competency-based question series designed chapter-wise to enhance your conceptual learning and understanding. Question 7. A constant magnetic field B is equal to 1 Tesla acts perpendicularly on a static square copper coil of 100 turns with each side of 10 centimeter. The coil is removed from the magnetic field within 0.5 seconds and then again replaced in another 0.5 seconds. We need to calculate the average EMF that develops in the coil during the entire motion that lasts for 1 second. So let's see the scenario. This is the square coil and the side of the square coil is of 10 centimeter. So we can find the area first. Area of square coil, it will be 10 centimeter multiplied by 10 centimeter. And it's better to convert it into meters first. So that will be equal to 0.1 meter multiplied by 0.1 meter. And it will be equal to 10 to the power minus 2 meter square. So this is the area of the coil. And we can see that the magnetic field is directed perpendicularly. It means the angle between area vector and magnetic field is 0 degree. So flux associated with the coil phi 1, it can be calculated as NBA, where N is number of turns. So there are 100 number of turns and the value of magnetic field is given to us as 1 Tesla and area of the coil we have calculated as 10 to the power minus 2. So when we solve it out, it will become 1 Weber. So when the coil is inside the magnetic field, the flux associated with it is 1 Weber. Now, in the second scenario, we have taken this coil out with some velocity v in 0.5 seconds. And when this entire coil is moved out, then there is a change in flux, and that change in flux has led to the creation of induced EMF, and that in turn has created the induced current. So now when this coil is completely out of this magnetic field region, the flux phi 2 will be 0. So flux has been changed from some value that is of 1 Weber to 0. And because of that, current is induced. So induced EMF, it can be calculated as, let's take it as E1. It will be equal to minus phi 2 minus phi 1 divided by delta t. And that will be equal to minus 0 minus 1, because phi 1 was 1. We have calculated the initial flux associated with the coil as 1 Weber divided by delta t. And this all entire process has taken place in 0.5 seconds. So we should divide it with 0.5 seconds. Finally, we will be getting 1 divided by 0.5, that will be 2 volt. So in this first case, when the coil is taken out of this magnetic field region, the EMF developed is 2 volt. Again, in the next 0.5 seconds, we are again taking this coil back to the magnetic field. So earlier, the flux is 0 when the coil was outside. Now we are taking it inside. So again, there will be the flux associated with it, and there is change in flux. So final flux, when the coil is completely inserted inside this magnetic field region, it will be again NBA, and it will again be 100 multiplied by 1 multiplied by 10 to the power minus 2. So 1 Weber. Again, we can calculate the EMF induced, that will be minus phi 2 minus phi 1 divided by delta t. And this entire process has taken place in 0.5 seconds. So we can write it minus 0 minus 1 divided by 0.5. That is phi 2 minus phi 1. So it will be minus of 1 minus 0 divided by 0.5. Because phi 2 we will be taking it as the final flux. The final minus initial divided by delta t. It will come out to be minus 2 volt. So we can see that during the process of taking this coil out from the magnetic field, the EMF generated is 2 volt, and when we have reinserted it, it is minus 2 volt. So average EMF induced, it will be the average of these two values, and it will come out to be 2 plus minus 2 divided by 2. Again, it will come out to be 0. So the average EMF induced, it will be 0. And we can also solve this with the help of common sense, that since the value of number of turns, magnetic field and area vector is not changing, and we are taking the same time for taking out this coil and again reinserting back into it, the flux change will be, the rate of change of flux will be same. So whatever be the current generated in the clockwise direction, the same current will be generated in the anti-clockwise direction, making the average current or the average EMF to be 0. Let's take part B of this question as well. It says, find the net thermal energy dissipated in the coil during the entire motion, and the resistance of the coil is 1 ohm. So we have observed this thing that E1, it was 2 volt. So during outward motion, and we can find out the energy dissipated heat, it is V square upon R multiplied by T. Here V is the voltage and it is E1. So it will be 2 square divided by 1 multiplied by 0.5, because the entire process of taking outward the coil, it has taken place in 0.5 seconds. So in place of T, we will be writing 0.5. So it will come out to be 4 multiplied by 0.5, that will be 2 joule. And for inward motion, again, T2 was calculated as minus 2 volt. So we can find out the heat dissipated as V square upon R multiplied by T. The entire process has taken place in 0.5 seconds. So it will be minus 2 square divided by 1 multiplied by 0.5. And it will come out to be 4 multiplied by 0.5. Again, we will getting 2 joule. So total energy dissipated will be equal to 2 plus 2, that will be 4 joule. So the energy dissipation will be 4 joule, but the average EMF induced in the coil will be 0 volt. Thank you. Keep learning, keep practicing, keep excelling.